To understand why it's important to prove that congruence in geometry is an equivalence relation, think about all the times that we want to use, say, the transitive property, that if A is congruent to B and B is congruent to C, then A is congruent to C. Well, that's a property of an equivalence relation. So there are three things we are going to prove, all of which are helpful. The first one is the reflexive property, and that says that A is congruent to itself, right? Some object A is congruent to itself. And symmetric says that if an object A is congruent to object B, then object B is also congruent to object A. Now, we don't use that one quite as often. That's kind of rare. And then the last one we use all the time is the transitive property. So I'm going to do this. It's true for all congruence relations. I'm going to do it for segments and show that. So first up in reflexive, let some segment AB exist and be arbitrary. All right, so by the way, why can we do this? It's important to remember your axioms, right? So axiom 5 says that at least 3 non-collinear points exist, so there's 2. And axiom 1 says that between any 2 points, a unique line is on them. All right, now the distance postulate says, hey, there's a real number r that's equal to the distance between these endpoints of the line segment. Now, it's important to notice this difference, right? When I put the bar over AB, it means the line segment AB. When I just write AB together, it means the distance between AB. All right, so that's an important piece of notation we use. It'll be important to understand that as we go forward. All right, so we have this. Well, going the other way, I have a distance r, and that's the distance between A and B, so I know that AB is congruent to itself. Why? Because the definition of congruence is that the line segments have the same distance between their endpoints. Okay, so not too bad, and we will use the reflexive property of congruence quite often. Symmetric, so now we need 2 line segments, right? So I have an arbitrary line segment AB and another arbitrary line segment PQ. Now notice that this is the same justification. We know that at least 4 non-coplanar points exist by axiom 5. Axiom 1 says that between any 2 points there's a unique line, so we get here just fine with our axioms. And we want this congruence to be true. We're saying that, hey, we've got 2 line segments and they are congruent. And then by the distance postulate, we know that this distance between A and B is equal to this distance between P and Q. And both of them, by the distance postulate, are equal to some real number r. Well, once again, in the reverse order, if we have a distance r and that's equal to PQ, which is also equal to the distance AB, then I know that PQ is congruent to AB. All right, now this one is a little different. So notice that here I am going to take 3 lines to be arbitrary, right? I need to show that if segment AB is congruent to segment PQ and segment PQ is congruent to segment XY, that AB and XY are congruent to each other. Now, I will point out that our axioms don't say that there are 6 lines in the geometry. All right, but I put a note next to axiom 5 in the course packet that you should notice. It explains everything, right? We're guaranteed by axiom 5 to have 3 non-collinear points, right? And then by axiom 1, there is a line that connects all 3 of those points. So there's at least 3 lines. That's just reasoning from axioms 1 and 5. But what does the ruler postulate say? The ruler postulate says that every single one of these lines has the property that, say, starting from this point, I can go exactly r units away, any real number I want, and there's a point there. So that means that, and that's the ruler postulate, which is axiom 3. That means that every single line has infinitely many points, and we know there are at least 3 lines, so there's infinitely many points in the geometry, and also since there's infinitely many points, and between any 2 points there's a unique line that connects them, we now also know that there are infinitely many lines, right? Any of the lines here that connect, right? So there are infinitely many points and infinitely many lines, so it's perfectly legit to say, hey, let these 3 line segments and these 6 points be arbitrary. Okay, and we're doing what we said. We're saying, hey, assume that AB is congruent to PQ, assume that PQ is congruent to XY. Now, by the distance postulate, since AB and PQ are congruent, we know that there's a real number, R sub 1, that measures this distance, the distance from A to B and the distance from P to Q, which are equal. And we know by the definition of congruence that there's a second real number that is the same as the distance from P to Q and X to Y. And I think you can see where we're going here, that we have the reflexive property of congruence. So we know that PQ is congruent to PQ. Well, if the distance PQ is equal to R1 and the distance PQ is equal to R2, then R1 and R2 are equal to each other. And therefore, we know that we knew that AB was equal to R1, but because R1 is equal to R2, now we know that XY also equals this real number. Therefore, the segments AB and XY must be congruent. And that completes the proof.